Imagine if every time you went to Starbucks and ordered something, they made everybody's order like from scratch. So if somebody ordered a coffee, they'd actually go and weigh out the beans and brew the coffee. So the next person, they want a latte, say? Okay, well now you've got to go weigh out the beans, brew the coffee, milk the cow, get the milk, to add the milk. So you can see that it doesn't make sense if you had to make all these different components from scratch every single time. Similarly, when we're making solutions in the lab, we don't want to have to make everything from powder every time, because that involves weighing things out, measuring, mixing, waiting for it to dissolve. If you want to do a different do pHs, then you have to pH test it, and all of these different steps you're adding error because you're weighing out different like small amounts of things. So basically we don't want to do that. So instead we make stock solutions. So just like Starbucks has its different, like the syrups that it mixes into its coffee or whatever, like you wouldn't want just the syrup by itself, right? That would be like super sweet. So we wouldn't want to actually use like a salt at like 3 molar or whatever, or 5 molar NaCl or whatever. We wouldn't want to do that, but we would want to dilute it into our solution. So just like adding the syrup to the coffee. And so we can have, when we make solutions, we can have stock solutions of like pH buffers, salts, metal things, all these different things, and we make them ahead of time. And this time, no matter what solution we want to make, assuming it contains those components, then we just have to mix and match the components and then add water to the volume we want. And we can calculate the amount of the various components to use using that C1V1 equals C2V2. Super handy. And then if there's another component we need to make, we can just make that, and then we just have to make that one component as opposed to having to make every single thing from scratch. You wouldn't be wanting to weigh out a teeny tiny little weight of something, because then you have like higher inaccuracies, like how accurate would be like a difference of like 1 drop of water if you were measuring out a teaspoon compared to if you were measuring out like a swimming pool. It's a much bigger difference. And so when you're making these like high concentration solutions, if you're a teeny bit off on your measuring, it's not a big of a deal as if you were measuring a really tiny volume. And so this helps, making these solutions ahead of time helps to kind of reduce the errors and keeps you from having to add really tiny amounts of stuff. Another great thing about stock solutions is typically when you have a really high concentration of something, it prevents like bacteria and fungi and mold and stuff from growing, especially when, as I show you, we like filter them first. And so this allows us to keep them like at room temperature instead of like in the cold room or in the fridge. So we can just keep them out and keep them pre-made. Whereas for like dilute solutions, so once you make like your working solution, so it's going to be more dilute. It's easier for things to grow in there. But you don't have this problem with your stock solutions. But you don't, there are some things that you can't just keep out and can't keep like your stock solutions out. And so things like this are like DTT, so like a reducing agent. So we can make stock solutions of that at like 1 molar and then freeze that, or we can add the powder fresh. And so we can make these solutions to order and then add those fresh components that are going to like oxidize or degrade or something over time. So like we add the antibiotics to our media at like the last minute because we don't want that to degrade before they can actually work. We add the reducing agents like the DTT, the BME and stuff. Like we add those like at the time. And so first we make up all these solutions and then we can add the things, we can mix it together and add it and make that all fresh whenever we want a solution. We can also do things like if we have, so sometimes it's good to have like these individual components as is. But we can also do things like, so like, you know how you might see those like pre-mixed cocktail packs or whatever. I don't even know what's in cocktails. I don't drink, but like my dad used to get like margarita mixes or whatever. So that would be, you can think of those as kind of being like a mixture, like a just add water type of thing, or just add alcohol. I don't know seriously, I don't know what's in those things. But anyway, so I do something similar. So I have like common buffers that I use. So a buffer is we typically call like all our solutions buffers, even though technically the buffering part is like the pH buffer that we put in it. So like tris or potassium phosphate buffers or HEPs. I have various ones. But we typically, so we call basically just like any solution a buffer, usually if it contains some sort of buffering agent in it. So we talk about like purification buffers. So there's different buffers that I use at different stages in my purification. And so I have like my like cheat sheets where I have the ingredients in those, and so you can see that. So like for a no salt buffer, I just add tris. For a high KCl, I have tris and then I have the KCl, and you can see that I'm using my stock solutions to make my working solution, so the one that I'm actually going to put my protein in. When determining like what concentrations you want to make, you typically want to make like a high concentration so that you don't have to add very much, because you don't want to add very much so that you have plenty of room to add whatever else you want to add. So if you made like a really dilute syrup, if Starbucks made like a super dilute syrup for their drink, then they'd have to put in like, their drink would be like 50% syrup and then like only 50% coffee, and then it wouldn't be coffee enough, and that you wouldn't have enough room to stick in enough coffee to have enough coffee flavor. So it's good to have a higher concentration of the thing. For some things, like my insect resuspension buffer or whatever, I pre-mix the tris and the KCl because I'm going to use this a lot. And so every time like I resuspend insect cells or whatever, and so I can make like a 10x working concentration. So by 10x, that means that this is 10 times more concentrated than I actually want to use it at. So this means that if I wanted to make 100 mils, I would put 10 mils of the 10x and then 90 mils of water. If I wanted to make 200 mils, it'd be 20 plus 180. Did I say 10 to 100? I would use 10 mils, add 90 of water to get to 100 mils. So typically what I do would be add 10 and then fill to 100 in like a graduated cylinder and then filter it out. If I wanted 200, I do 20, fill to 200, so that'd be adding 180 of water, and then filtering it out. When you make the so it's a lot easier to mix them to make solutions when you just have to add like these liquid components, and so you can easily calculate how much of the various components to add using that C1V1 that I've talked about. You have to start with the solid though to actually like make these stock solutions. And so when we do this, we're going to rely on the molecular weight or the formula weight. The formula weight is going to be the weight of a mole of those things. So if you wanted a 1 molar solution, so you need to weigh out 1 mole's worth. And so to know what 1 mole's worth is, you look at the label. If I looked at the the formula weight for sodium chloride, you can see it's 58.44 grams. So that means if I weighed out 58.44 grams and put it in, I would get 1 molar of sodium chloride. That would dissociate into sodium and chloride, but it would mean 1 mole of sodium and 1 mole of chloride. Whereas if I put in like 1 molar of sucrose and I weighed it out based on the sucrose, I would get 1 mole of sucrose, but that sucrose would still be like intact sucrose. It wouldn't dissociate into fructose and glucose. Molarity is a measure of concentration I've talked about before, and it talks about like how many copies of something per liter in moles. So a mole is 6 times 10 to the 23rd copies of something. So it's like a dozen, but it's way, way bigger than a dozen because we're talking about really, really tiny molecules. So we're talking about big numbers of them in a really concentrated volume. So 1 mole means 6 times 10 to the 23rd molecules of something per liter. And so our stock solutions, we're often talking about like molar or millimolar, and then in our working solutions, the concentrations are typically more in like the millimolar, micromolar, nanomolar even ranges. So for imidazole, we have a molecular weight of 68.08. So if I weighed out and dissolved 68.08 grams of imidazole and then dissolved it in up to 1 liter of volume, I would get a 1 molar solution. If I wanted 2 molar imidazole, I would double that. And so I keep like a cheat sheet of things that I make a lot with already having calculated the various amounts to add. when you go to make a solution, typically what I do is, so I weigh it out. So you want to make sure that when you're weighing it out, you're like zeroing or tearing or whatever the scale. So you can use like different size weigh boats or whatever for what you need, but make sure you zero it, so you're not weighing the weight of the weigh boat. And then you weigh it out. And then, so what I typically do is, so if I want to make a 1 liter, I'll take a 1 liter beaker. I'll fill it up to about 750 mils, and then I'll start pouring in the liquid, and pouring in the solid, and slowly, depending on how fast something dissolves. So you don't want to just like stick the solid and then pour the liquid on top, or else just the solid's gonna kind of just like clump up, and it's gonna be really hard to mix. So you have your liquid. Make sure you put it in the stir bar, so like the magnetic stir bar. And so sometimes you might be like, why isn't this stirring? And it's because you forgot to put in the stir bar. And if you put in the stir bar, but you have like all your solid junk at the bottom, it's not gonna really stir. So be careful about that. And also be careful of like big chunks. So try to like pound it up a little first if there's big chunks. And to avoid having big chunks, make sure that you keep the lid sealed tightly, because if water gets in, then it can cause that clumpiness for some of the things that are like hygroscopic, so they like suck in the water. But anyway, so you don't want to fill the water all the way to the line. Firstly, because those lines are only approximations, remember, so you could easily overshoot. And second, because the solid you're adding is going to add volume. And so the final volume is going to be more than the amount of water that you had in there. So typically you want to do this, so you add your typically I'll add some and I'll let it dissolve, and then add a little more, let it dissolve, add a little more, let it dissolve. That'll also help with preventing it from like just clumping up and kind of like giving up trying to dissolve, it seems. But you want to do that, make sure it dissolves completely, and then you want to actually get the correct measurement. So then I would pour it into a graduated cylinder, and fill the cylinder up to the volume that you want. These are not for measuring. These are approximate values. So these are really great if you're wanting to like dissolve your liquid. So normally I'll start off like mixing in one of these with like a stir bar on a plate, but do not trust these volumes. These are approximate volumes. If you want, when I actually do the measuring part, I use a graduated cylinder. And so these lines, you'll see like the closer, you want to use the graduated cylinder like closest to the size that you're measuring, because so here like the lines are 10 apart. If I wouldn't want to use like a 1 liter one if I had a really small, like less than 100, like if I had like 100 mils, because this is like, here the lines are 1 mil apart, and so I can get a better like accuracy in my measurements. So yeah, so those are approximate volumes, and the lines on here are also, the ones on like the beakers are approximate, and the ones on the flasks are approximate. Even the ones on the graduated cylinders are still like, they're not perfect. If you want like super precise, there are things like volumetric flasks you'll use a lot in chemistry. We don't use them as much really in biochemistry because we don't need to be that precise. But these, so you'll see like with the graduated cylinder, you have all those different options for different volumes that you want. With a volumetric flask, you only get like a single volume. So you have like a 1,000 one, you'll have like 100 one or whatever. So there's different sizes, but they're for different specific set volumes, and they have like this single line. So you can see that like they have this big flask part, and then they have this narrower stem, and this line is like calculated to be super like calibrated to be super precise. So if it's at the line, it'll be exact. Plus or minus 0.3 mils for this. So that's pretty good. And remember when you're measuring, you want to you measure from the meniscus. So if you're looking at it like straight on, the water, because the liquid, it's going to kind of curl up the sides, because it's really sticky, so the water like sticks onto the surface, and it kind of like pulls up as it's dragging along the surface. because it's like attracted to the surface and it's pulling up, and then it's pulling the water with it, the rest of the water with it, because the water is attracted to it, other water. So basically that's why you get like that meniscus. And so you want to go from the bottom of the meniscus should be on the line. So like if you have my chin was the meniscus, I'd want the chin to be on the line, measure like that. At this point, it's time to filter them. So you don't always have to filter your solutions, but I tend to just like always filter my solutions. So I use this like vacuum filter. So it comes in like these 3 pieces. So you have this part, you have this part, and you have this part. And this is like a reusable one. And so basically this part, it has this like rubber gasket. Make sure it has the rubber gasket on it. Like we had our old rubber gaskets, they like broke, and then apparently you can't just like buy the rubber gaskets. So we had like our machine shop make rubber gaskets, but then they're a little too big, and so then it's kind of like hard to get the right seal. But this part screws on. Then this goes in here. And then you have to put your membrane on top. So that's actually going to do the filtering. And so this part is like single use. And so these are like nitrocellulose membranes. These are like 0.2 micromolar or micrometer. See, I always like just default to molar when I see a micromolar. Okay, but anyway. And then this base part. So you want to hold down the base. This is hard to do like one-handed, but you want to hold down the base before you screw it on, or else, as you see, this isn't going to be tight, even though this bottom part might be tight. You want the whole thing to be tight. Okay. Okay. So now this whole thing is tight. Then I can hook it up to the vacuum line. See, I already filtered this morning, so that's why I have this all, it's already done. But this goes in here, and then when you turn the vacuum on, you'll hear the noise. And then typically what I do is I pour a little of the liquid in to make sure it goes through nicely, and the vacuum is all good, and then pour it in and filter it completely. So you can see that the liquid is flowing through the filter nice and slow. So I have a nice seal here, thanks to the parafilm. So there should be like a stopper here, but those things like come off all the time. But yeah, so if this wasn't tight, then it would be, the water would be like flowing all out of here. So that's why I usually pour a little in first to test that you have a good vacuum seal. Then you should get a nice flow through. You also, if like this part's not sealed well, you'll get like a crazy really annoying noise. Sometimes if there's a chip in the top of the bottle, you'll get a bad seal. In those cases, what you can do is you can like take a piece of parafilm and wrap it like around to try to get a better suction. So these things only hold like 500 mils, so if I want to make a liter, I have to like fill it part wise. Vacuum filters aren't compatible with like all volume or flasks, so like these have like a narrower head, so they're not gonna match. But so like they work with all like the various sizes of those other like Pyrex bottles with those like big orange caps. So yeah, so just make sure that you know that before you try to use it. With these bottles, there's a couple things you want to keep in mind and be aware of. So first is that the cap. So when these caps get old, they like get autoclave too many times. So the autoclave is like the sterilizer thing. It's like this really hot, really high pressure oven thing that sterilizes. And if you do it too many times, these caps can get really crusty, and then this can kind of start flaking off. And if it flakes off like into your nicely filtered buffer, then that's gonna make you really sad. And so check the lid, and also check the rim of the bottle. It shouldn't be cracked, and it should have this plastic seal on it. If it doesn't, then it won't form a nice seal with like your vacuum filter. For instances where we need to be like super sterile, and we are like for like tissue culture and that sort of thing, or when we're filtering our like insect cell, like our V1, so big cell, like insect cell viruses for protein expression, we'll use these like vacuum filter units that come like, they're like pre-sterilized and stuff, and they're like single use, and yeah, so they can screw on to the other bottles as well, but they also have to come with like a little bottom attached, and so it works the same as those others. They're just like single use, pre-sterilized. For some solutions, when you don't have as much volume, then what I use is I can do a syringe filter. So we have a syringe, you pull up your liquid, and then use a filter. So we have different size filters for these. So typically when I'm doing like an antibiotic or something like that, when I'm just doing a smaller portion, I do like a 0.2 filter. So it's good to use, like I typically use the 0.2 filters for various like little solutions, whatever. And then when I make those things, then I can like store them in the freezer. If you are looking for like specific examples and working out some of the calculations, I will put a link to the blog articles with more.